So I'm really pleased to welcome and introduce our second speaker, who's Jinming Zhuang from University of Pittsburgh. He's a PhD student there, and he'll present on CHARM, a framework for composing heterogeneous matrix multiply accelerators for Versal ACAP devices. So Jinming, if you want to go ahead and take the share. And again, I'll invite anyone who has a question during this session to post in the Q&A, and we'll get to that at the end.
Yeah, sure. Can you see my screen?
Yeah, looks good.
Yeah, thank you. Thanks, Castle, for the introduction, and thanks, Mario, for the nice talk, which will definitely make the following presentation clearer. Anyway, hi, everyone. This is Jinming Zhuang, a third-year PhD student at the University of Pittsburgh, supervised by Professor Pepe Zhou. I'm very excited to share our work in the first AMD HACC Tech Talk, titled "The Charm Composing Heterogeneous Accelerators for Matrix Multiply on Versal ACAP Architecture." This work is a collaboration between the University of Pittsburgh, UCLA, UIUC, and AMD Research Lab. So I want to begin this talk with a brief background story. When we first got the Versal VCK190, we were very surprised by its high computation capacity and energy efficiency, as the manual could tell it can achieve up to 6.4 teraflops FP32 throughput under only tens of watts of power. Then we start to deploy the real end-to-end transformer-based applications on the VCK190, expecting to achieve the high performance and energy efficiency. After several months, we found it actually non-trivial to sustain the throughput of 400 AI engines on VCK190. We're mapping the application with both large and small matrices like the Vision transformer shown here. Our first version implementation only has 49.5 G-flops throughput. After another several months, we identified the bottlenecks and proposed CHARM, which provides a 32.5x gain in throughput. You may wonder how we managed to do so. Before entering into the bottlenecks and proposed methodologies, I will make a quick introduction to the Versal ACAP architecture. So Versal ACAP is a 7-nanometer fully software programmable heterogeneous computing platform featuring a general purpose processing system, the programmable logic, and the dedicated AI engines. Each AIE here is a 7-way very long instruction word supported vector processor with a 32 KB local memory in AIE version 1. For our target device, Versal VCK190, there are a total of 400 AI engines. And to sustain these 400 AI engines, the communication between AIE array to the other component is through the 39 I/O tiles at the bottom of the AIE array with a maximum 1.2 terabytes per second bandwidth. The AIE, PL, and the CPU can access the off-chip DDR4 DIMM memory through the network on chip with up to 25.6 gigabytes per second bandwidth. This is because in VCK190, there is only one DDR4 bank, but actually the capability is up to 102.4 gigabytes per second, which can be utilized in VCK 5000. However, the high computation capacity and the limited off-chip bandwidth brings us the first challenge. So as we can see in this following chart, compared with the previous FPGAs, the U250 16-nanometer data center board and the 28-nanometer VC709 FPGA, in terms of computation scaling, the throughput of VCK190 under FP32 data type is 4.3x over the U250 FPGA and 14.8x over the VC709 FPGA. However, the off-chip DDR4 bandwidth of VCK190 is 1/3 of U250 and about 85% of VC709. So that means careful data orchestration is needed to make full use of the computation capacity of the Versal VCK190. To solve this challenge, we hugely explore the on-chip data reuse to cover the time consumption spent on off-chip axis. So here's an example. Assume that we are dealing with a matrix multiply with a large size. The data is first stored in the on-chip memory on the device side. The DMA on the PO side will first load a bulk of data in the left-hand side matrix and right-hand side matrices from the off-chip memory to the on-chip buffer, either the BRAM or URAM. And due to the data reuse characteristic of matrix multiply, the small piece of data in the on-chip memory can be reused by the AI engine array for computing several times. At the same time, when the data is loaded from the on-chip memory to the AI engine and for computing, another bulk of data can be transferred from the off-chip memory to the on-chip memory and be overlapped by the computation. Therefore, exploring the on-chip data reuse can amortize the huge gap between high computation capacity and the limited off-chip bandwidth for large matrices with good data reuse. However, keeping this unified accelerator design that provides high throughput for large matrix multiply is not enough. For example, if the application has layers with small matrices, in order to use the accelerator design before, the quickest way is we simply do host pending in the off-chip DDR memory, where the valid data is marked in the DDR space. Then, with the same hardware configuration that utilize a huge amount of on-chip buffer in PAO and a huge amount of AIEs, it will introduce both invalid communication and invalid computation. This will extremely hurt the overall system throughput. So to make it clearer, we showcase a series of results when mapping the square matrix multiply under AP32 data type on a design that leverages 384 AI engines with over 80% utilization of BRAM and URAM. In this chart, the x-axis shows the different square matrix sizes, and the corresponding throughput, the real onboard throughput, is showing in the y-axis. When the size is large, for example, here 3K by 3K by 3K, as shown in point A, by hugely exploring the on-chip buffer reuse, we achieve 2.8 teraflops per second throughput. However, at point B, where the matrix size is 64 by 64 by 64, because of the shape mismatch between the huge computation resources and the small matrix size, it only gets 0.4 gigaflops throughput. So in this work, we propose an idea to compose multiple diverse accelerators together. By designing specialized accelerators for large and small matrices separately, it is capable of avoiding the huge amounts of invalid computation and communication. To systematically analyze how many accelerators we should design for an end-to-end application, as well as how to partition the hardware resource to each accelerator, we also provide analytical models and an automatic flow to do the design space exploration. So in a short summary, we provide a white box open source framework to aid the programming effort for matrix multiply based system level design. It can also be a good reference to guide the design of other applications. From the design challenge aspects, we hugely explore the on-chip reuse to sustain nearly 400 AI engines with the given off-chip bandwidth. We also propose a two-step search algorithm to improve the overall throughput of the system when computing applications with both small and large matrices. Next, we will describe our charm compilation flow in detail. So charm takes the matrix multiply based AI models, for example, the BERT, MLP, VIT, the one-time DDR bandwidth profiling results, the hardware constraints, including the number of POIOs, number of BRAM, URAM, AIEs as input. By leveraging the backend compilers, the AIE and V++ compiler for AIE and PL, the GCC cross compiler for ARM CPU, it can generate the bitstream and host executable files then can be directly deployed on board. So this flow can also support the VSK 5000, which is a data center Versal board, by just change the host code a little bit. And the main part of CHARM consists of 4 components, including the single accelerator design space exploration, the diverse accelerator composer, the runtime configuration, and the automatic code generator. When composing several accelerators together, the composer will sequentially launch the single accelerator DSE to find the hardware configuration for each accelerator. The CHARM runtime configuration is responsible for guaranteeing the right execution order for all the layers. The CHARM automatic code generator leverages the information from the composer and the runtime configuration to generate the corresponding design code for AIE, PO, and host CPU. Then in the following part, we will highlight the CHARM single accelerator design space exploration and the diverse accelerator composer. When doing a single accelerator design, we follow a bottom-up strategy from the single AIE to AIE array, the PO, and to the whole system. So for the single AIE design, by digging into the hardware architecture, we make full use of the very long instruction word capability. Since we also apply the double buffer technique to the AIE local memory, for matrix multiply, the time spent on data transmission from the PO to AIE can also be overlapped by the computation. Thus, in the following example, we assume our data is already loaded into the AIE local memory, and we demonstrate the processes of data movement and computation between the local memory and the AIE register to show how the AIE can run efficiently. Assume that here we have 4 vectors of 4 elements in the left-hand side matrix, which is L0 to L3, and we have 2 vectors of 4 elements of right-hand side matrix, that is R0 and R1. So we allocate 4 vector registers in the AIE core, that is A0, A1, B0, B1, and we also allocate 2 accumulation registers to store the temporary result on the AI engine core. And we illustrate our single AIE design by showing each time step in the pipeline. In cycle 0, we preload 2 vectors into the AIE register. So here we load L0 to A0 and R0 to B0. And so that's in the cycle 1, while loading another vector of data, that is L1 to the A1 and R1 to the B1, we can also do a vector MAC operation on the preloaded data in cycle 0, which is the L0. Actually, here should be the here is the L0, the column of the left-hand side matrix times the 1 element of the right-hand side matrix. And then to cover the latency of accumulating the temporal results on the same accumulation register. So imagine that if we calculate the L0 times R00 in cycle 1, and then we go to L1 times R01 in cycle 2, then it leads to the accumulation to the same accelerator, the accumulation register 0. But actually, for the floating point operation, it is hard for us to do the MAC and write the same data to the same register. So instead, here, we will add a latency hidden step. So we involve another MAC operation to calculate data in accumulator 1 instead of accumulator 0, so that we can cover the latency by ending back to the same accumulation register. Then, to avoid the frequent register evasion, we will store the data from the accumulation register here back to the local memory in cycle n-1 after all the reduction dimension is finished. And in this pipeline, we make full use of all the computation resource since there are no bubbles in the MAC operation stage. And to ease the programming effort, we provide a template with high computation efficiency for matrix multiply, supporting matrix size that is multiple times of A times A times 2. Instead of writing 100 lines of code every time, user can just input 3 lines of code to indicate the size of the matrices. The single kernel efficiency is demonstrated here when using different matrix size in a single kernel. We choose the 32 by 32 by 32 as our single AI design for its high memory utilization and computation efficiency. Compared with the work HGCN published in FPAO 2022, our 32 by 32 by 32 single kernel achieves 2x higher efficiency. And then when scaling out to the AIE array, the number of ports connecting PO and AIE, namely the PO IO, could be the bottleneck, especially when nearly 400 AIEs are utilized. The IOs in the AIE array can send data from one port to multiple destinations through 2 mechanisms, which are the broadcast and the packet switch. The main difference between these 2 mechanisms is when using the broadcast, the same data will be sent to different destinations at around the same time. For packet switch, the different data will be time multiplexed and sent to different destinations at different time. In this work, we hugely explore the PO-IO reuse by combining these 2 mechanisms together. The following example shows how we send the first row of the left-hand side matrix to compute with the right-hand side matrix by using the combined mechanism. For illustration purpose, the right-hand side matrix is preloaded into the AIE local memory. So here, in time 0, data 0 row of the left-hand side matrix will be broadcast to the 0th row of AIE, and then in time 1, the data 1 will be broadcast to the first row of AIE array. And the same thing happens for data 2 and data 3 to row 2 and row 3. So far, we have demonstrated how we use a single PO-IO to send data to 16 AI engines by using the combined broadcast and packet switch mechanism. Based on the aforementioned design methodology, we built an accurate analytical model to guide the real implementation for the single accelerator design. The information of the layer that mapped to this accelerator, as well as the hardware resource that allocated to this accelerator, will be fed into our model. It can generate the estimated throughput and the hardware configurations. For example, the AIE array parallelism and PO-IO reuse strategy. Then, based on the aforementioned single accelerator analytical model, we propose the diverse accelerator composer to compose multiple accelerators together and to boost the overall throughput. This diverse accelerator composer solves the problem of how can we assign multiple layers within one AI model to multiple accelerators. When solving the problem, we set the number of accelerators as a hyperparameter and use a 2-step algorithm, including the workload assignment and the hardware resource partitioning to solve that. We use an example to illustrate the composing processes. Assume we have 5 layers in the model, which need to be mapped to 2 accelerators. To reduce the algorithm to polynomial complexity, we first sort the order of the layers by the number of operations in each layer. And then, for this example, we add 1 block to assign the layer to 2 accelerators. Here, layer 3 to accelerator 1, the rest of the layers to accelerator 0. Then we partition the hardware resources proportionally to the total number of operations assigned to the corresponding accelerator. After that, our Charm diverse composer sequentially launches the single accelerator DSE to find the hardware configuration for each accelerator with the specific parallelism strategy, and will give us the estimated throughput and the overall throughput. Next time, it will change another workload assignment strategy to find an optimized design. Then this should be the result of composing two accelerators. Remember that we have a hyperparameter for number of accelerators, right? So the composer will explore the hyperparameter of the number of accelerators by adding more blocks here, and it will try to find other better solutions if exist. So so far, that's about how Charm can design an optimized single accelerator and how to compose multiple accelerators together. Then let's look at our experiment results. So for our single accelerator design, we compare the design implemented purely on the PL of Versal using the AutoSA with Charm, compared with the Charm single accelerator design on AIE. The multiplication of the pure PL design is implemented by DSP 58, where one DSP can handle one FP32 MAC operation directly. And we achieve 5.5x and 1.9x gain on the throughput and energy efficiency. And for our single accelerator DSE, we verify its accuracy by changing the size of the square matrices here. The throughput estimated by our analytical model has less than 5% error rate compared with the onboard real implementation results. When the matrix size is 6K by 6K by 6K, Charm achieves 3.2 teraflops real onboard throughput. After further optimization on the AIE array connections, currently we provide 4.2 teraflops onboard real implementation throughput, which is also integrated in our latest GitHub repo. And by using the combined broadcast and packet switch connection, we can easily allocate 384 AI engines without any POIO overutilization or routing congestions. And we also apply our Charm framework to 4 applications, including the BERT for natural language processing, the VIT for classification, NCF for recommendation, and MLP for regression or classification. So we visualize the characteristics of the applications here to help explain our results. The exact size of each application here can be found in our paper. For BERT, there are 6 relatively larger layers and 2 types of batch matrix multiply, or we call multi-head attention, containing 96 smaller layers within each type. So here, obvious shape variance can be observed in BERT. For VIT, the shape variance is even larger in terms of the variance in both the size and the number of larger and smaller layers. For NCF and MLP, the larger layer dominates the operations in the application. So here we will demonstrate the throughput comparison among different Charm strategies, including the 1 monolithic accelerator, 1 specialized accelerator, 2 diverse accelerator, and 8 duplicate designs. During exploration, Charm will automatically cover these strategies and find the best configuration. Here, the 1 monolithic design is a general solution that can handle application with the matrix multiply with arbitrary sizes. And we leverage the single accelerator DSE to find the specialized hardware design for each application. They're called 1 specialized accelerator design. The 2 diverse design is a representative setting found by Charm. The duplicate design applies the same methodology as AMD DPU, which puts several accelerators with the same configuration together. So for the BERT and VIT, the best strategy is the two diverse accelerator design, which achieves 5.3x and 32.5x gain over the corresponding one monolithic design, since they both have huge shape variance. And because of even larger variance in this VIT, the gain is as expected higher. For NCF and MLP, since the larger layers dominate the whole application, so the one accelerator design becomes the best strategy. And Charm achieves 2.94 teraflops throughput for the MLP. And here we also include some fancy pictures to show our real onboard implementation layout. I like these layouts a lot, especially when saying that the chip is almost utilized and we can successfully rotate. So thank you for your listening, and thanks for the invitation from Cathal on behalf of AMD. And our paper is published on FPGA 23, and our code is open sourced on the GitHub. There is a QR code you can scan for our GitHub repo. And now we'll come to any questions. Yeah, thank you again.
Great, Jinming. Thank you very much. I saw a question, but it looks like it was disappeared. I see it's been partially answered. So the question was, is there any provision for a folding mechanism to reuse the AI engine in scenarios where a large data flow graph doesn't fit in the hardware at once?
Is this still on the chat list?
Yeah, it's in the answer at the bottom. So Mario has given his take on that. But feel free if you'd like to add a comment on that.
Which are large. So I guess that means so far we have 400 engines. If we are dealing with large data flow graph, sure. So if there is a large data flow graph that contains many of the layers and maybe exceeds 400 engines, which means one layer cannot even be mapped to one AIE, then the purely spatial design doesn't work. But we can always use some temporal strategy, like several layers mapped to multiple AIEs. So we can mix the spatial design with the temporal design. Is that that address the question? So we mix the temporary design with the spatial design so that it can fit on the AI engine.
Yeah, I think that's great. Thank you. So we're just over time, so let me sort of move to close. But just before I do that, let me find the right screen and I'll share again. So I'd like to thank everybody who joined the session today. And before I close, I'd like to invite you to join our next HACC Tech Talk, which is on July 17th. You can see the details on the slide. We will have two presenters again, Dr. Linghao Song and Dr. Tobias Kenter. I see Tobias is on the call, so I look forward to welcoming him back. So those topics will cover gradient solvers and sparse matrix multiplication for FPGA HBM accelerators, which are also part of our HACC clusters. So you'll find registrations on the HACC webpage again, where you registered for this session. I'd like to just thank both speakers again for two great talks, and to everyone who joined, and particularly people who asked the questions. A reminder that you're very welcome to apply to join our HACC program and get access to the type of heterogeneous compute hardware that we're talking about, and engage with the community of HACC researchers. So all the people who ask questions, if you'd like to follow up on any of those topics, HACC is the place where you want to do that. So you can find details on the screen on the webpage. So with that, I'll close, and thanks again to everybody who joined.